Hello everyone. Today we'll be learning about the haloform reaction. The haloform reaction is a pretty commonly seen reaction in Orgo 1. It usually starts off with some form of a methyl ketone. So, just as a reminder, a ketone is essentially a carbonyl group with two different groups that aren't hydrogen. This is our methyl group. This is the other random constituent that we would have in a ketone. It's usually reacted with a dihalogen. So let's say X2 for now. A strong base, so let's say sodium hydroxide. And then the second step would be to treat it with an acid. So let's use hydronium for now. These two compounds are in excess. Excess meaning it will just keep reacting with itself, or it will keep reacting with the starting material until the product desired is formed. In lab, this would just mean adding much more of this than you would of this or this. So, the actual mechanism is pretty simple and it's quite repetitive. The important thing is to draw out the hydrogens in this methyl. Instead of X2, let's choose chlorine gas. Chlorine gas and sodium hydroxide would choose to react first. So the hydroxide would take its lone pairs, attack this hydrogen, which would reform a double bond over here, followed by this breaking of this double bond to form an oxyanion. It would look something like this. Now, you don't need to know this in Orgo 1, at least where I did my undergrad, but in Orgo 1, in Orgo 2, you will learn that this is called an enolate. Essentially, an enolate is a negative charge directly conjugated to a double bond. By conjugated, I mean no more than one carbon away. So, an enolate is also a weak/moderate nucleophile. Because it's a weak or moderate nucleophile, this double bond will do some chemistry and act as a nucleophile and attack one of our reagents that is present over here. Now, as I mentioned earlier, these compounds are in excess, so just keep this in mind when I explain the next couple steps. So, our site of chemistry, or where we want to rearrange, should start off with this negative charge, because this negative charge prevents us from having a stable compound. So electrons will be pushed from this oxyanion, which will then leave in turn the site of reaction to be this double bond. This double bond will then attack chlorine gas, which would leave this with a chloride ion. And our resulting structure would look something like this. Now, recall the starting materials, sodium hydroxide and chlorine gas, are in excess. So this would again repeat to do the same exact thing. The hydroxide from the sodium hydroxide, which will come, attack this hydrogen, do the same exact chemistry, push electrons, form an enolate. Then rearrangement would occur, where this enolate would then go and attack this. Which will in turn help us form this dichloro kind of thing. Now we're left with one more hydrogen. And guess what? The chemistry still remains the exact same. So this hydroxide will go and attack this, form an enolate again. I can kind of skip the last step because I assume you guys should get the memo. Oops. Now at this final step, you'll kind of need to do some fill in the blank chemistry. What I mean by this is you see that there's a trichloro group. Obviously, it might not even be a trichloro group. It could be any halogen. But We know that halogens are very good leaving groups. We have 3 of these right here. So we can kind of predict that this trichloro group gets kicked out of the molecule. But that leaves us with a plus charge over here. Well, we know that our sodium hydroxide, which is the base that we use, is in excess. If it's in excess, it would evidently react with the alpha carbon, which would help us form our final product, which is a carboxylic acid. But our trichloro group is still unstable. And as we know, this is an acid catalyzed reaction. So the hydronium would get a proton picked up. And the final result of this haloform reaction would be a carboxylic acid and our new and improved trichloro group. Thanks for watching.